This meeting is being recorded.
In problem 4 from chapter 21, we are asked to draw the two enolates resonance structures that can be formed upon treatment of a strong base on these ketones here. So we have 4 ketones, and then our life structure is actually an aldehyde. So we'll see things progress pretty much the same, even with an aldehyde versus a ketone, but let's take a look here and see how we generate these two resonance structures. So our first ketone here in A, if we were to deprotonate this, we could grab either side here at the alpha positions. We could grab a proton. So I'll show you what that will look like here using our sodium hydroxide base. What happens initially is that lone pair gets deposited here on this carbon and would generate a negative charge there. But then through movement of that lone pair, we could form the pi bond seen here. And then we'll kick some of those electrons up from that carbonyl onto the oxygen. So we're going to end up with 3 lone pairs and now a negative charge on this oxygen here. After we do those 2 movements of electrons from the first resonance structure. So this is our answer for A, the 2 resonance structures shown with the curved arrows from 1 to generate the second. Let's take a look at what happens with structure B here. So at this alpha site, we do not have a proton to deprotonate this cyclopentanoate. So let's deprotonate over here. So we'll grab that proton with our base. We'll move that lone pair onto this carbon right here. So that will be our negative charge on that carbon. Then we'll see through movement of these electrons onto the ring, and then these electrons from the carbonyl onto the oxygen. The first move, we generate the pi bond seen here in orange, and then the second movement generates the negative charge on that oxygen atom, and this will be our resonance structures here for these 2 enolates. Next, we have structure C. So once again, we only have 1 alpha position that is not occupied with other groups. So over here, we would remove a proton. So let's show that. So we'll deprotonate. Those electrons will go onto this carbon here. So we have a negative charge on the carbon to the left side of our carbonyl. Then we'll move those electrons and we'll generate the second resonance structure with, again, 2 curved arrows. First move will generate this pi bond here, and then the second move causes the lone pair to move on the oxygen, and then we have our negative charge on our oxygen shown in our second resonance structure. So this is the answer here for part C. All right, let's keep moving. Now we have part D here. Again, the alpha position over here is occupied by the phenyl substituent, so we can only deprotonate over here. Nice and easy. We'll grab that proton. We'll move those bonding electrons onto this site right here. So we have a negative charge now on the carbon to the right. We're going to move those that lone pair in to form this pi bond in our first move. Then we'll kick some electrons up onto that oxygen, and now our second resonance structure will have a negative charge on the oxygen, whereas the first had the negative charge on the carbon. And this is our answer for part D. Now, I mentioned early on that this is, excuse me, our last structure is now an aldehyde instead of a ketone. We can't deprotonate this proton here on the left, so we'll have to choose this only one here. That's on the right-hand side, so we'll grab that. That will generate a lone pair right here and a negative charge on that carbon that I just dotted in orange. So now we're going to move that lone pair. Oh, not there. We're going to form a pi bond right over here. So we'll move the lone pair to this area here, and then that will generate our last structure after we move those electrons from the carbonyl onto this oxygen. And we can see now with 3 lone pairs that oxygen will have that -1 charge. And these are our 2 resonance structures for the enolates for our aldehyde in structure E.